Okay, great. Well, thanks a lot for putting together this exciting workshop, and apologies for not having been here yesterday. I had to give a talk in Dresden yesterday, so I didn't follow what was presented yesterday, but I think I know roughly what Gerrit's been talking about, so I'll try to be a little bit complimentary on the experimental side and show you all the difficulties that you have to actually realize the systems that the theoreticians come up with. So since this is a tutorial, I'm going to go through a very broad introduction to spin transport in magnetic materials, starting with metals and then going to insulators, and then also show you a little bit about the properties of insulating ferrimagnets. I mean, you know, these things don't just fall from heaven. You actually have to make them on purpose, and that is not always super obvious. And then the main part will be really thermal spin transport in insulators, and it's the role of bulk effects and interface effects. And I'll show you that both the bulk as well as the interface to a neighboring metal are important in order to understand the signals that you measure. And finally, just a few words about spin transport in antiferromagnets, because that's quite hot, as you saw in the talk before. Since this is a tutorial, I rely quite a lot on collaborations with colleagues in Munich, now in Dresden, with Gerrit and people in Tohoku, with theory people in Konstanz, Ulrike Ritzmann, who's now here, and for the materials fabrication with Caroline Ross's group at MIT and the TU Kaiserslautern next door. So yeah, just a very basic, how does spin transport in magnetic metals work? So if you have a normal metal like copper, you have the same number of up and down electrons, and they are equally scattered, which means the current is equally carried by spin up and spin down electrons, and so you have an unpolarized current. Now, if you put a magnetic material, a magnetic metal such as cobalt, then you have a net magnetization. And now what happens is that the electrons at the Fermi level that have the spin which is parallel to the magnetization, like the blue ones here, they're scattered little. But the electrons with the spin anti-parallel to the magnetization, the red ones, they are scattered a lot. So this means the current is primarily carried by electrons with a spin that is parallel to the magnetization. And so you have a spin polarized current. So that is very important, because it means that the electrons at the Fermi level, even though they are not the ones that carry the magnetization, they still have a net polarization, which can be anything between, you know, a few percent to 100% in a fully spin polarized material. So how can you use that? You can actually use that by generating pure spin currents. So here is a device which consists of a ferromagnet, this gray thing here, and a non-magnetic material such as a copper line or graphene line here. And now what we do is the following. We inject a combined spin and charge current from the ferromagnet into this paramagnet, into copper. And this, of course, generates spin polarized charge carriers in the copper. But the spin accumulation generated also diffuses down here, and there is no net charge current. So if you have pure diffusive spin current that can then be absorbed by a second ferromagnet, and in this second ferromagnet, the absorbed spin current can be used to transfer the spin angular momentum to move a domain wall. This thing here is a domain wall, which now moves to the left. So you have a net spin transport, but no net charge transport in this metallic system. So this is what it looks like if you simulate this. This was done as software by Thierry Vallée that you heard yesterday. So here we inject the charge current, and you see that the spin accumulation diffuses equally down and up. So here we have the net spin accumulation diffusing down, even though there is no net charge current. And if you plot this logarithmically, it looks very fancy. And you see even there is some spin accumulation that goes into the ferromagnet here. Right, so this is in metals. For transport at the Fermi level. So this is done really by injecting currents with a voltage, so the electrons are really, really close to the Fermi level. You know, they usually move at the Fermi level. However, you can also generate electrons that are not diffusive at the Fermi level, but that are faster by going above the Fermi level. So this is an experiment we did some time ago, where we hit a sample with an infrared laser pulse to take electrons from the Fermi level and one electron above the Fermi level. And then these electrons above the Fermi level, they can be extremely fast, because there's few of them, they don't scatter as much, they can be, you know, super diffusive. And so what we do is we measure here the domain structure, and in a scattering experiment from this domain structure we get a scattering ring where the radius of this ring just gives you the size of the domains. And now we measure how this superdiffusive spin current alters the spin configuration, so the magnetization pattern, the domain structure, as a function of time. And we see that this ring here, that the ring here changes its radius and its intensity. You see here initially it has a radius at, this blue line here at 34, and then after 200 femtoseconds it has like 33, so the radius has become slightly smaller, which means the spin structure has changed. And the interesting thing is, if you look at it, it really happens on a few hundred femtosecond time scale. So this is something which is very exciting because it can be super fast. You can change the spin structure at 300 femtoseconds using these superdiffusive spin currents. So that's something that we're doing as part of this collaborative research center together with Kaiserslautern. It's essentially, it is limited by the spin diffusion length in this metallic materials. And that can be rather short for these highly excited electrons. The spin diffusion length, or this superdiffusive spin current, only gets like a few nanometers, a few tens of nanometers. The ones at the Fermi level can get to maybe like 100 or a few hundred nanometers. And the problem is that the spin currents don't get very far because there's lots of other electrons to scatter with. And I'll come then in the future also to ways to transport the spin over longer distances by getting rid of the electrons. So how about insulators? Obviously you don't have free electrons that can carry the spin, but we have magnons. So we have a coupling of localized magnetic moments, and these can actually be used, these magnons, to manipulate a domain wall as shown here. And they can also propagate. This is a very nice example from the group in Kaiserslautern. So you have here all your spins, and now initially you excite them all in phase and everything, nothing propagates. But now you see that we decide to have them go out of phase, and you see there's a spin wave propagating across your sample. So you're really transporting spin angular momentum that propagates in your sample, even though there is no free electrons. It's really a magnonic spin current. And the nice thing about these magnonic spin currents is, as I show you later, that they can propagate over much larger distance, so tentatively like millimeters or hundreds of microns, so really macroscopic distances, which in a metal is absolutely not possible. So let me now start and add to our magnetic material a second material on top. So here we have our magnetic material, which say is YIG, and now we put something non-magnetic on top like platinum. And now we look at the interaction between the charge transport in the platinum and the magnetization in the YIG. So all the current is flowing in the platinum, and so this is an effect which was co-discovered by Sebastian Gönnenwein. And what we do now is we measure here the change of the resistance in the platinum as a function of the magnetization direction in the YIG. So here is the sample, platinum on top of YIG. And now if we inject a charge current into the plane of our sample, so here in this direction, then due to the spin Hall effect, this generates a transverse spin current. So electrons with spin right are scattered to the bottom interface, and electrons with spin left to the top interface. Now these electrons here that have a spin pointing to the right will start to interact with the magnetization. So if there is a finite angle between the S and the M here, then there will be a spin transfer torque, so a transfer of spin angular momentum. And this means there will be an enhanced dissipation in the platinum, and so the resistance of the platinum will become larger because the spin current here can really enter the insulator. So the magnonic spin, it can generate a magnonic spin current in the insulator and change its resistance. Now if we have the magnetization parallel to the spin accumulation direction here, then you see the angle is 0. And if it's all parallel, there can be no net transfer of angular momentum, and therefore there's reduced dissipation. So you have a smaller resistance. And so this was measured by lots of people. So there's an original paper with Garrett, Nakayama et al., and Chen et al. So many people have measured that. There's also a review on that. And essentially, you get an angular dependence of the resistance that's just a cosine squared of the angle between the magnetization direction here and the direction of the spins at the interface. And this is what it really looks like. So you can vary the angle in plane, and you get this cosine squared dependence. You can vary the angle out of plane, and you get a cosine squared dependence. And only if you vary the angle, let's see here longitudinally, then it's flat. Because then, of course, the magnetization is always pointing in a direction that is perpendicular to the direction of the spins at the interface. Because the spins at the interface pointing in that direction, and if the spins at the interface they point in that direction, whether the magnetization points this way or that way, it's both times 90 degrees, so it makes no difference. Okay. So this is just to show you that the charge transport in a metal adjacent to a magnet can actually be influenced by the interaction with the magnet, even if it's an insulator. So now let's come to the thermal part. So as you already heard from Gerrit, you can generate by thermal gradients, you can generate spin currents. So it's the simplest picture, it's just the boiling of spins. So you generate more spin excitations, more magnons at the hot end, and therefore they will diffuse in all directions towards the cold end. And so there are lots of theory papers about that, and I guess you heard from Gerrit about the details. And so this is our easy picture. So you have a hot end where lots of magnons are generated, and they move then to the cold end. So now I just want to give you a very brief overview of what has been done in the past and what are the challenges, what is easy and what is tough. So originally there's a paper by the Troco group, by YIG Temperature group. They measured the spin signals generated by thermal gradients in conductors here and then in insulators. And then in 2011, there was a lot of debate about the investigation of YIG platinum interfaces, whether you have some parasitic interface effects, and I'll go into detail in the next couple of slides how we can distinguish between parasitic interface effects and the real spin-Seebeck effect. And then there are also new materials such as these semiconductors measured in the Ohio group. And there are many, many active groups in Sendai in Japan and in all over the place. So this now become a very interesting field, which really started only like, less than 10 years ago, and now you have many, many people that work on that. So what are the challenges? So the first problem is that depending on the geometry, you can have poorly controlled temperature gradients, and I'll show you what these problems are in detail. And the second problem is that there could be parasitic interface effects. That's the problem problem 3. And then there could also be spin caloric or charge caloric effects if you have not insulators but metals. So these are 3 problems that we need to fix. And then there are open questions such as the dependence of the spin-Seebeck effect on the magnon spectrum, interface effects, and the spin-Seebeck effects in ferrimagnets and antiferromagnets. And finally, can we make the spin-Seebeck effect useful? And NITT means not in this talk. So this is the one thing I'm not going to talk about because we're physicists. So whether you can make this useful or not is something that is very important, but it's not my business. Right. So let's come to the first problem. So the original geometry is a very obvious one. You take your substrate, you put a ferromagnet like permalloy on top, and you put some detector layers here like platinum, and then you just put it in between a hot and a cold end. So we heat this end and we cool that end, and so we have a net temperature gradient across. And then you expect that it should be a net spin current flowing, and the spin current should then be detectable by a charge current by these lines here. And this is really what the thing looks like. So this was built by Andreas Kehlberger during his PhD. And I'll show you a lot of results which you have never seen before because they were never published, because we just found that they're very, very difficult problems to overcome in order to understand the signals. So here we had the hot and the cold end, and so so the idea was that, okay, if you have the spin current flowing along the temperature gradient, then the generated spin current that enters the platinum will generate a charge current that you can measure as a voltage due to the inverse spin Hall effect. So now this is what it should look in theory. So you make it hot here and you make it cold here. However, and then you measure and you think you got a hot wire here and a cold wire here. However, you measure it really in like a helium bath. You measure it in a cryostat or at air, which means that air cools it everywhere. And this means you got like cold up here, cold here. So there's not only a temperature gradient from left to right, but there's also a temperature gradient from up to down. And that's really shit. So why is that shit? Because you also get charge caloric effects. You just get the anomalous Nernst effect because you have now the magnetization and the temperature gradient and the measured voltage, which can be perpendicular. So you get this, so you're in a symmetry where you can have an anomalous Nernst effect, and you get nice signals. You know, they're not beautiful, but you know, they look very much like what we thought we would expect. However, the symmetries don't fit. So this first big problem is you got temperature gradients the wrong way. So then we tried to put like a second layer on top so that the layer in the center is symmetric. It never really worked. And the problem is you can really not control the temperature gradients sufficiently well, at least in our experiments. And I know there are people that work very hard on that in Bielefeld and Regensburg. And they, you know, they found that, you know, it's just super tough in order to get the temperature gradients perfectly in the plane. However, there's an easier way. You just change the geometry. So then we went to a new geometry where what we do is we where we apply the thermal gradient in the vertical direction. But before that, let me just show you how we make the samples. So here's a paper if you're interested. So we grow yttrium iron garnet on GGG, which is a substrate, and I'll show you in a minute what this is. And then we do some in situ surface cleaning before we put the platinum. And then the good thing is YIG is a super good insulator, has a very high band gap, and the platinum on top means all the current only flows in the platinum. And so in the following, we always use the longitudinal geometry where the temperature gradient is in the vertical direction. And this is a happy student that sees that his sample is being deposited by PLD. So this is really the work that you have to do. You have to deposit these samples in the UHV PLD chambers. And this is YIG. So Garrett might have shown you that YIG is a monster. So this has a very complex unit cell. And it has two sublattices, two ion sublattices of ions, which are octahedrally. Oh, did I get? Maybe I should switch off my wireless, otherwise I get into trouble. Okay, okay, so you have ion atoms which are tetrahedrally coordinated or octahedrally coordinated, and they couple antiferromagnetically by superexchange, so you really have a ferrimagnet. And this grows really nicely. So this is here an example where we grow such a ferrimagnet. Here it's gadolinium, not yttrium iron garnet on GGG. And you see that it's, you know, a perfect growth. And within one unit cell, you change from GGG to YIG or GIG. So this is really like something that grows nicely. And it's quite amazing because, you know, the unit cell of YIG has many, many atoms inside. It's really complex. But it just shows you, if you have a compound that nature likes, it's also easy to make. Most often, the problem is that the compound we are interested in tends to be the one that nature doesn't like. So very often, for instance, in oxides, nature likes to have a certain oxide, like in a chromium oxide. There's a ferromagnetic oxide, CrO2, but nature prefers Cr2O3. So you have to really trick nature into getting the right material to work. But with YIG, it's really like YIG loves to grow the way it grows. And then you do some X-ray diffraction, and you check, and you see that the YIG is pretty much has the peak at the right angle, which means that the lattice constant of YIG is pretty much the one that you expect from literature. And we get, you know, very nice reflectivity data showing that we have smooth interfaces and smooth surfaces. Right, and so what do we do with the sample now in this longitudinal configuration? We actually put your sample in between a hot and a cold end. So here we put something which is hot on top and something cold at the bottom. And now you don't have the problem that you have temperature gradients going all over the place, because really the temperature gradient is perfectly up to down. Okay? And that just is because the lateral extent of our samples is rather large, so that really the temperature gradient at the position where we measure it, it's perfectly perpendicular, so you don't get all these problems with temperature gradients going the wrong way. So this then generates a spin current. And the spin current then, depending on the direction of the magnetization due to the applied field, will lead to a charge current due to the inverse spin Hall effect that we can measure. And this is really what it looks like. So here's the hot end, this is the cold end. You put your sample in between, and then you measure with the contacts across your sample the voltage. And in order to measure this voltage here, you need a material which has a large spin Hall effect, a large inverse spin Hall effect, and then we do some additional measurements, as we're showing here, to get a material that has a large, nice spin Hall effect, such as platinum. So the important thing is now with the longitudinal geometry, so having the temperature gradient perfectly vertical, we don't have the problem that the temperature gradient goes some uncontrolled way. So this fixes one of the problems. And we can measure the signal as a function of the applied in-plane field direction, and we see a nice sinusoidal fit, and we can probe the magnetization, both the transverse and the longitudinal component. So now the next question is there a possibility that the signal originates from an interface effect? You know, so far our theory is it's really the temperature gradient in the bulk of the sample that generates a spin current, and the spin current goes into the platinum and generates the charge current that we measure. However, there was a lot of debate with some colleagues at Johns Hopkins that claimed that you have a polarization, so generation of ferromagnetic platinum, so you polarize due to proximity, affect the platinum, and then you can also have charge caloric effects. And to check that, what we did is we varied the YIG thickness, the ferromagnetic thickness. Ferromagnet thickness. And the reason is very simple. If it's an interface effect, the interface doesn't care if you got another meter of material below. Whether you have like 50 nanometers or 500 nanometers, the interface can be the same, and so it should not depend on the thickness of the ferromagnet. But quite obviously, our spin-Seebeck signal depends very strongly on the thickness. So really, the signal here originates from the bulk. Now the question is, why does it show this thickness dependence, so this increase and then saturation? Well, the referees came back for the paper and said, like, well, it's a change of the material properties of the ferromagnet, like the damping or the saturation magnetization. But no, it's pretty constant in the range of thickness that we look at. Furthermore, so this means that really it cannot be due to this. So we've solved the problem of the uncontrolled temperature gradients by the longitudinal geometry, and we solved the problems of charge caloric effects by using an insulating magnet, and it's really not a proximity-induced interface effect, as we know from this thickness dependence. So really, there's a really genuine spin-Seebeck effect exists, and it really took like 5 years to figure that out. I mean, you know, somehow luckily, initially when the first measurements were done, it turned out that it was right, but it's really something where you have to be careful, and it's worth hanging in there in order to show that really what you measure is what you think you're measuring. Because quite often you can measure some effects that are really parasitic, and you need to take care and change and vary things in order to make sure that you understand what you're really measuring, because in the end you just get something out of your measurement setup. All right, so we have this intrinsic spin-Seebeck effect that that exists for the longitudinal geometry in YIG platinum. Now the question is, where does this kind of increase in saturation come from? So there we turn to our theory partners in Konstanz, and there are also now a lot of other theories by Garrett's group and Jaroslav Jakovniak and people from Groningen and Rembert Deune. So the theory here is that suppose you start with a thin ferromagnet. So here this is the ferromagnet, this is the platinum, and you have a temperature gradient, you generate magnons, they go into the platinum and generate a charge current. Now if you make more and more ferromagnet, then initially more and more magnons are generated that go into the paramagnet and therefore generate the charge signal. So the signal should go up. Yeah?
What do you mean by more and more ferromagnet?
So, oh yeah, thicker and thicker. You put more and more, so you start just with the platinum, and now we add just a little bit of ferromagnet and more ferromagnet, even more, and even thicker and thicker. So initially, if you have, let's say, only this much ferromagnet, you only generate, this magnon here. Now you add a little more ferromagnet, and we also generate this magnon here that also adds to the signal. So as you go thicker and thicker, the signal goes up. But eventually, now we add another meter of ferromagnet here, but all the magnons generated in this end here, which we just added, they don't make it to the platinum. They get scattered already here. So that means eventually it has to saturate, because if you add another meter of material here, it's not going to affect the spin current that enters here. And so it's, sorry, the temperature gradient is here.
Is it the same as you increase the length, or?
Yeah, okay, so of course you have to have the temperature gradient, you have to keep that constant. Absolutely, yes. So as you increase the thickness, more and more magnons reach the interface, but effectively you have a finite reach of these magnons, so the signal has to saturate, and you can do this more properly. So there's a theory by Ulrike Ritzmann and Uli Nowak's group, and they did micromagnetic, well actually they did Heisenberg spin field simulation, atomistic spin simulations, and they measure the spin accumulation due to the gradient. For this type of gradient, then they make it thicker and thicker and thicker, and you see the signal goes up and eventually saturates. And this is exactly what we see in our measurement, and we get an effective reach for our magnons, an effective propagation length of the magnons of a few hundred nanometers or a few microns, depending on the material that we use. So this works really well, and means there is really a spin-Seebeck effect. Now, the next question is, what is the role of the bulk? And what is the role of the interfaces for the size and the temperature dependence of the signal that we measure? So to look at what the role of the bulk is, what we did is we varied the bulk. We just have different YIG thicknesses going from a 100 nanometer sample to a single crystal that is really like, I don't know, 3 millimeters thick. Or I don't know, how thick is our bulk system? Like millimeter, something like that. Yeah, so it's really super thick. All right, so and then we measure just the signal as a function of temperature, and we see, oh wow, there's a huge change. If you go from bulk to a thin film, the signal size changes, and you see also that the this non-monotonous dependence on the temperature changes. So really there's a lot of changes that have to result from the bulk, because what we do is we always put the same platinum on top. Same condition, same platinum, so it has to be bulk. So now we can plot this position of the peak temperature here as a function of thickness, and we see this peak temperature as we go from bulk to thin films goes to higher and higher temperatures. And also we see that the peak becomes smaller and smaller. You see here's a proper peak, and here was not much of a peak left. Now, there was one discussion, one argument in a paper by colleagues from Sendai that claimed that it has to do with magnon-phonon drag. So this can be because magnons and phonons can interact, and of course if you measure just the thermal conductivity or thermal conductance of a sample, you also see such a temperature dependence due to the phonons, which show such a temperature dependence because they're frozen out here, and here just get umklapp scattering. So at first it looks very similar. You think, oh, it must be magnon-phonon drag. However, if you look very closely, you see that here for different thicknesses, there's virtually no change in the peak position, whereas here we get a huge change in the peak position. And also the temperatures simply don't fit for the peaks. So this means the phonon-magnon coupling does not dominate our low temperature spin-Seebeck effect enhancement. So where could it come from? So there's some very nice simulation that you probably saw from Garrett, done by Joe Barker and his group, where they measure the magnon dispersion relation for YIG as a function of temperature. And well, the first thing you see is that there are two types of magnons. So there are magnons with one direction and magnons with the other direction, so that increase or decrease the magnetization. And if you look at the temperature dependence, you can see that the red line here is just the KBT, which goes up. And you see that this line here, with the opposite direction of the magnon, so the increase in the magnetization, comes down in energy, and eventually you populate that. You see initially all the magnons that are below the red line are, like say, red magnons, but eventually also you populate the blue magnons here, so you can have a temperature dependence that is non-trivial. Another test that we did is we applied strong fields, because if you have a strong field, what you can do is you can freeze out magnons. At very low temperatures, 1 Tesla corresponds to something like 1.3 Kelvin. So at 10 Tesla, you can freeze out magnons below like 15 Kelvin. And so what we did is we did this measurement at 300 Kelvin, where you actually shouldn't expect anything, because at 300 Kelvin, the amount of magnons that you actually freeze out are tiny. It's just really a super low energy magnons. But it turns out there's a strong suppression even for 300 Kelvin measurements. And that tells you that the magnons that you freeze out, these low energy, long wavelength magnons, contribute significantly to the measured signal. So this means it's not all magnons that contribute to the signal the same, but you have these long wavelength magnons which contribute significantly, even though they're only a small fraction of the total number of magnons present at 300 Kelvin. So, and you can explain this because if you look at the magnon propagation length as a function of the frequency, you see that the low energy magnons, the long wavelength magnons, they propagate very far, whereas the high energy magnons don't. So in particular for the magnons generated far away from the interface, only the long wavelength magnons actually arrive at the interface. So it's important to note that magnons of different energy, of different frequency have a different propagation length. But of course, normally we induce a full spectrum of magnons, but the ones that arrive at the interface from far away are the low energy magnons. So you have this reduced suppression at low temperatures, and this is because you have an increased propagation length that counteracts the field suppression. And of course, eventually when you go to super low temperatures, like 10 Kelvin, there you expect a huge effect, because at 10 Kelvin, you obviously only populate magnons below 10 Kelvin. You can completely freeze those out. So at very low temperatures, again, they should be at 2%, but at the moment, you can only let them to about 30 Kelvin. So important take-home message, as Olena described it, take-home message is the magnet distribution can be manipulated by magnetic fields. So now let's go from YIG, which is a simple material, relatively simple because it just has two sublattices, to the next more complex material, which is gadolinium iron garnet. And in gadolinium iron garnet, we now have three sublattices. You've got two iron sublattices and the gadolinium, which also has a spin moment. So we have now the A side iron, the B side iron, and the C side gadolinium. And the A side and the D side iron, they couple antiferromagnetically, just as in YIG. And the D side iron and the C sides are here, and the C side gadolinium and the D side iron, they actually couple also antiferromagnetically. So you have, in the end, three different exchange couplings, this one, and that one. And the important ones are this one and that one. Now, and now, depending on the temperature, now different sides can dominate. Because at low temperature, the gadolinium orders and has a very large moment. But at high temperature, it's really the D side ion that orders. And you see they're antiferromagnetically coupled, which means that the total magnetic moment is different at low and at high temperatures. And this can be seen here in this paper from 1996, where you measure the total magnetization as a function of temperature. And if you look, so this is gadolinium iron garnet. See, there's a huge moment at low temperature, and then it goes down, goes through zero, and then comes back up again, but in the opposite direction. Let me just show that to you again. So here, below the compensation temperature, the gadolinium wins. It has the largest moment. So the total magnetic moment of our gadolinium iron garnet is in the direction of the gadolinium. So if you apply a field, the gadolinium will align with the field direction. Above the compensation temperature, so up here, you see the gadolinium is very small, so it's really the D side ion that dominates. And then you can see that now, it's, if you apply a field, the D side ion actually aligns with the field direction, but the gadolinium is pointing in the opposite direction. So if you go across the compensation point, really the full lattice turns around. All the spins turn around. This one goes to this goes to that, and this goes to that. And now we measured the Seebeck effect, and we saw that, oh, this looks very complex. You see, at high temperature, we get a similar signal to YIG. At intermediate temperatures, we get the opposite sign. And at even lower temperatures, we again get the opposite sign. So this is very, very difficult. Initially, we thought it's all wrong, and maybe there's a problem with our sample. And so the question is why? Why do we see that? So this is now our spin-Seebeck signal as a function of temperature. See here at this compensation point, we see that our signal of the Seebeck, the spin-Seebeck signal also changes sign, and that's relatively easy to understand because you see going from here to here, everything turns around. Now this goes to this goes to that, this goes to that. So of course the signal has to change sign. Very simple. And this was actually predicted by Onuma in Toko and JEA, and they said that okay, you should have this minimum in the magnetization, and you see a sign change of the spin signal, what we see. Good. However, it turns out that's not the full truth, because you go to further down in temperature, you get a second sign change. We really thought that cannot be, because you see at low temperature, because if you go to lower and lower temperature, then of course the magnetic moment just continues to go up. You see here between 150 and 50 Kelvin just goes continuously up. So really the signal does not mirror the magnetization. And so we thought, it cannot be true, we don't believe it. We asked our colleagues to measure as well. So these were our measurements. Then we asked our colleagues in Japan to measure. See, they see the same thing. We asked our colleagues in Munich to measure. They see the same thing. So this is very nice, because we have 3 samples grown in 3 different labs, measured in 3 different labs, grown on different substrates, grown with different methods, all shows the same thing. So now, I believe. It's probably a real effect. So now let's think about where it comes from. It's a nice collaboration, which also ended up in this, all-stars paper with 20 authors. And but we need to find out where this comes from, and then you need people like Garrett to help us out. And they, his group, Joe Barker, calculated the spectrum of gadolinium iron garnet, and you see again at low energies, you have only the red magnons of one direction. And then you have, at higher energies, you've got a magnon gap and then magnons with the opposite direction. And now you can think how, as a function of temperature, the total magnon spin current can change sign. So low temperature, you see here's KBT. Only the red magnons are occupied. You see only red magnons, only one sign. At intermediate temperatures now, you see that the KBT goes up. You start to populate also blue magnons. And if you populate enough blue magnons, they will actually completely compensate the red magnons, and you have 0 net spin current, because this number of this magnons and this magnons is the same. And at even higher temperature, then the blue magnons win, so the spin current changes its sign. And this is what we observe here. So this is one of the explanations that can tell you why we have a change in the sign of the spin current. But of course, this is a pure bulk effect. It means that, okay, in the bulk, the net spin current can change sign as a function of temperature in these compensated ferrimagnets. So then we thought, like, okay, well, let's measure also different capping layers on top. So we put platinum, palladium, and tungsten capping layer on top. Now we keep the ferromagnet identical, and we only vary the interface and the capping layer. So that's very important, because now we probe only the interface effect. The bulk is now always identical. And we see, okay, for tungsten and platinum, we got the opposite sign, because the spin-Hall effect has the opposite sign. Fair enough. However, for palladium, you get the same sign as platinum. But what is obscure is that you see here there's a different peak position of this signal, so different temperature for the tungsten, for the palladium, and the platinum. So the question is, where can this come from? Okay, we have different amplitudes. That's easy to understand. But if it was just a different amplitude, you would just expect that the signal is scaled up, down, or scaled to negative values. But the fact that this peak temperature changes really is something that cannot originate from the bulk of our YIG, because it's the same YIG as before. So it was cut from one wafer, and it cannot be. The bulk is the same. Well, then people come and say, well, maybe the spin-Hall angle, so the efficiency of the conversion of the spin current to a charge current, has a different temperature dependence for platinum and tungsten. It's like, oops, yeah, maybe. Could also be that the spin diffusion length in the platinum and the tungsten has a different temperature dependence. So this is something to check. So to check that, what we did is we put a little bit of copper in between. So we have now YIG copper platinum, or YIG copper tungsten, and the platinum is still the same. The spin-Hall angle and the spin diffusion length, with or without the copper, should have exactly the same temperature dependence. So there shouldn't be any difference. However, there is a huge difference. Now compare copper, platinum, and platinum. You see here that the peak position changes again. Now you compare tungsten and copper tungsten. Again, the peak position changes. So really, it cannot be something that is due to the platinum, but there must be something at the interface happening. And so what we did is we looked at this temperature dependence in more detail, and we see if we now look at platinum and copper platinum, you see this is now rescaled, so they have the same peak height. Copper platinum has a peak at about 70 Kelvin, platinum at about 100 Kelvin. And now we look at platinum and copper tungsten, and we see that copper platinum and copper tungsten have a peak temperature roughly at the same temperature. So this means that even though the amplitude is different, the peak temperature is the same, so the copper seems to really dominate the temperature dependence. And so now we went to our friends that do imaging to actually look at what is really happening at the interface. What is the difference between YIG platinum and YIG copper platinum? And so what they did is they did high-resolution TM imaging, very nice, done in Glasgow by Donald McLaren. And you see here the YIG, and then here's platinum, and here's the YIG and some copper and platinum. And okay, you know, the YIG and the platinum is well defined. You get a smooth interface. And what they can do is a so-called electron energy loss spectroscopy. So what they can do is they can measure the elemental distribution, the platinum, the iron, and the oxygen, at the interface. And they see that at the interface here, the YIG has primarily iron. So there's more iron at the interface than oxygen. Okay, can be. Now let's compare to the YIG copper platinum. And we see here now in the YIG copper platinum that now at the interface we got more oxygen. So that is interesting because it means that the YIG, which is like a super inert oxide, at the interface has a different atomistic structure. And I would not have predicted that at all. For me, YIG, it's a typical, very nice inert oxide, and you don't expect anything to happen. However, it's not true. You can really see that even though it's a ceramic, it does change its interface depending on whether you put copper or platinum on top. And this, of course, now can also explain why, if we put copper platinum or copper tungsten, we get the same temperature dependence, because it's really the copper at the interface that changes the interface structure with the YIG. And the transmission of the spin currents, of course, depends on how the interface termination looks like. So this is something that I was very surprised by, but it makes sense in the end. So there is an interface-dependent transmission of the spin current across the interface, and really the capping layer influences the YIG termination. So now the next step that we did is we looked at gadolinium iron garnet and looked at different materials on top. Why gadolinium iron garnet? Well, remember, in gadolinium iron garnet, as a function of temperature, we could have the blue or the red magnons dominate. So by changing the temperature, we can see whether the blue magnons or the red magnons, how they go across different interfaces. So we put gadolinium iron garnet and with palladium and platinum on top, and we see that the first high temperature sign change is exactly at the same temperature, and that is simply because it's a bulk property of the ferromagnet, or the ferrimagnet in this case. However, the low temperature sign change is different at 55 and 82 Kelvin for palladium and platinum. And remember, the sign change tells you when the red or the blue magnons dominate. So here again, you have these red and blue magnons, the alpha and the beta mode. And you remember at low temperature, it's the alpha mode that wins, and at high temperature, it's the beta mode that wins. And if now this sign change here changes, it means that depending on the interface, one, the alpha or the beta mode, transmits across the interface better. So now let's compare that. You see here at palladium we have a lower compensation, a lower sign change than at platinum, and that means there's a weaker interface exchange coupling for the alpha mode in palladium compared to platinum, and this could mean that there is a more effective gadolinium-platinum coupling than gadolinium-palladium coupling, because really the beta mode, the higher energy mode, is the one that's primarily dominated by the gadolinium. So this is a nice thing about gadolinium ion garnet, because we can probe the alpha mode and the beta mode kind of separately and at least semi-quantitatively understand which of these modes goes across which interface better. And now we finally actually kept the same material on top, just platinum, but we actually had a different interface treatment. So what we do now, we deposit the same thickness platinum, but once we etch the interface before we put the platinum on top, and once we just deposit the platinum. And what we see is that the high frequency sign change is again the same. However, the low frequency sign change, that actually varies just by changing the interface. Same material, same thickness, same deposition conditions. We just did a little bit of etching at the interface first. And so this means this sign change shift is due to a change of the interface exchange coupling. And this means this can be explained by an increased damping or reduced transmittivity of the beta mode for the etched interface compared to the untreated interface, which means that the 3D ion spins couple less effectively to the platinum conduction electrons for the etched interface compared to the untreated interface. So really here the take-home message is that there's a strong correlation between the interface structure and the transmittivity of the different magnon modes. And we then, of course, again went to our friends and asked them to do some high-resolution imaging. This time this was done by Yuri Ivanov and Jürgen Kosler at KAUST. And we see, very nice gadolinium-gallium garnet, gadolinium ion garnet, and the palladium interface. And we looked again at this gadolinium ion garnet palladium interface with and without copper. And we see a little bit of palladium and platinum intermixing at the interface with the GIG. But if you look at the elemental distribution, you see that at the interface you have lots of gadolinium and lots of iron, but the oxygen is further below. Now you can really see here's the platinum, and really the oxygen doesn't go to the interface. It's really a platinum gadolinium and platinum iron interface, but not a platinum oxygen interface. So and here we are, of course, very interested in all the smart theory people in the room, that some quantitative theory of why a certain mode goes across the interface more efficiently if you have oxygen or no oxygen at the interface. That would be something that would be extremely excited to hear about. All right, just to show you that garnets are not the only ferromagnetic insulators or ferrimagnetic insulators that work, we've also looked at cobalt ferrite. Cobalt ferrite has some advantages because it has a simple structure compared to YIG. It's a spinel, it's not a garnet. It can have high anisotropy and magnetostriction. And so we made some of these samples. Actually, they were made by YIG together with a group of Katrin Dörr and Halle. And what we saw is you can make them rather smoothly. And then we measured the spin-Seebeck effect. And we find if you put platinum on the cobalt ferrite, indeed, we get a typical spin-Seebeck effect. And the spin-Seebeck effect signal follows the magnetization. And we can now also measure the temperature dependence. And you see here that we do see a change depending on the thickness. So it's again the bulk of the cobalt ferrite that dominates the signal. However, we don't see this low temperature enhancement that we see for gadolinium ion garnet and yttrium ion garnet. So really the material quantitatively changes the temperature dependence. Qualitatively, the signal is there as well. And in antiferromagnets, there were some interesting results recently, such as the observation of the spin-Seebeck effect in chromium-203. What they did there is that, as Helen recently, just before, explained, if you apply a strong field, the antiferromagnetic lattice is going to make a spin-flop transition where you get a net ferromagnetic moment. This happens above a field of something like 5 Tesla, and then exactly this is when you see the increase in the signal. So really, if you have such a signal and you're above the spin-flop transition, then the weak ferromagnetic moment generates a signal. That's not very surprising, but it was nice to see. So more interesting, though, is we looked at strontium iridate, where we see a signal, is something we don't understand completely yet, but it looks like even in materials where you're below, the spin flop transition, so you're still at a purely antiferromagnetic state, you see a signal, so that's something that needs to be investigated. And now, finally, a little bit about spin transport and insulating antiferromagnets. There was a lot of excitement about some results that showed if you put an antiferromagnet in between your YIG and the platinum, that you can actually enhance the signal. And if you measure the temperature dependence, people have seen that depending on the thickness of the antiferromagnet, the peak in the signal actually occurs at a different temperature. And this temperature always looks to be roughly about the nail temperature. And so the explanation here was, which I don't think at the moment anyone is completely clear about that, is that at the nail temperature you've got a lot of very loose spins. And they seem to transmit the spin waves, the magnetic spin current, extremely efficiently. And there were claims that even the signal with an antiferromagnet is higher than without. And that's something which we also see, but we don't understand it. So somehow there's an amplification of the spin current when it goes across an antiferromagnet close to the nail temperature. So there's some data from us. Right, and we looked at iridium manganese. We put iridium manganese in between. Again, you see there's a peak, and the peak temperature changes as a function of the iridium manganese thickness, because if you've got more iridium manganese, you simply have a higher nail temperature. All right, so I think time's up, so let's finish. So the most important people that contributed, so this is a recent group photograph, so it's really like Andreas Kehlberger, who started in my lab all the activities and who now got a proper job. Joel Kramer, who is doing a lot of work with Bo and Dong at YIG-JGU, was a postdoc. He did also a lot of work in particular on this temperature dependence and the ferrites. And I have 3 permanent staff scientists, Hartmut Zabel, Martin Johaler, and Gerhard Jakob. And Gerhard Jakob is really instrumental in all of what is the dependence of the thermal conductivity, because he's really a specialist for thermoelectrics and thermal conductance. And then we've got lots of great collaborations, so with the group of Uli Nowak and Ulrike Ritzmann, who's now here, in Constance, Donald McLaren in Glasgow for the TM imaging, with the group of Caroline Ross at MIT, Mehmet Onbasli, who's now somewhere in Turkey, don't know, hopefully. Timo Kuschel and the group of Günter Reis in Bielefeld, Sebastian Gönnwein, Rudi Groß, Stefan Geprex and Hans Hübel in Munich, Sebastian's now in Dresden, Yuri Ivanov and Jürgen Kosel at KAUST. And then in Tohoku and in Japan, Mr. Onuma, Joe Barker, Garrett Bauer, Eiichi Saito, Sadamichi Maekawa at JEA. And of course, nothing would work without the funding, in particular the InSpin project together with Garrett and a few people, and the SpinNet project together with Tohoku University and our Collaborative Research Center and the ERC grants. If you're interested, there's a nice review of ferrimagnetic garnets by a Russian. It's like 150 pages. Everything you wanted or you didn't want to know about garnets, you'll find that in there. And there's a review on spin-Seebeck effect by Garrett. And so to sum it up, so the spin-Seebeck effect, really the origin of the measured signals are thermal magnetic spin currents which are generated in the longitudinal geometry in the bulk ferrimagnet. It's not an effect due to wrong temperature gradients. It's not an effect due to charge caloric effect, and it's not an effect due to parasitic interface effect. So it's real. Both the bulk properties and the interface govern the temperature dependence, so both is important for what you measure. And in gadolinium ion garnet, we see these 2 sign changes at the magnetization compensation point and below, and different interfaces transmit the different magnon modes differently. And so spin transport can occur also in antiferromagnets with an amplification at the nail temperature. Very exciting. Don't think a lot of people understand the details yet. And here are some of the papers. All right. So I think time's up. So thanks.